Continuing our series on the 2016 GCSE physics paper from CCEA, the Unit 2 paper. And question 4 is electromagnetism. 4a. The oil industry pumps crude oil through many kilometres of pipeline. To measure the volume of oil flowing in the pipeline, an electromagnetic meter is used, and the diagram shows the basic construction of such a meter. So the oil comes down through here, it drives the little turbine, and the turbine has a magnet attached to it, and as the magnet passes this coil, it produces a little pulse in the coil, and this counter counts pulses of voltage from the coil. So basically each rotation of this turbine will cause the magnet to generate one pulse as the little magnet passes here. So full rotations of this turbine are being counted on this counter. So the flow of oil is going to determine the rotation speed, and therefore a certain amount of oil is going to come through here for each one of these rotations, and that's how they're working out how much oil has flowed. So you're explaining, it says here, how the voltage pulses are created. Okay, so this magnet moving near the coil creates pulses by electromagnetic induction. How they are used to measure the rate of flow. Well, basically, the speed of flow in this pipe will determine how fast this wheel turns, and so there must be some relationship between the speed of oil flow and therefore how much you're getting per second and the number of pulses you get per second. So the rate of oil flow affects the rate of rotation of the turbine wheel, and that will affect how fast the counts are going up. So the counts are going to be directly related to the flow of oil. So because the flow of oil is related to the speed of rotation, then the counts on the counter per second are going to also be related to the speed of flow. So there must be some mathematical relationship that they can use between the counts on the voltage pulses and how much oil has come down through the pipe. Part B, the diagram below represents the distribution network for electricity from the power station to users such as households. And you can see what we've got here. You've got your power station, you've got a transformer here taking it up to the transmission lines, and then when you get near to the houses you've got another transformer making it suitable for the houses. So we know that this one's going to be a step up to get to high voltage, and then this one will have to be a step down to get back to normal 240 volts that people would want at their homes. Power station generates electricity at a voltage of 15 kilovolts here. This is increased to 120 kilovolts by transformer 1. So we've got 15 and 120. Calculate the turns ratio of transformer 1 used to do this. So we use our turns ratio equation that the NS over NP value will be the same as the VS over VP value. So if we then put in the VS, V at the secondary is the 120 and V at the primary is the 15. And that gives us a value of 8. And although that's a voltage over a voltage, it's the same value as NS over NP, which is what we're trying to find. When the voltage is increased in this way, is the current flowing in the transmission cables AC or DC, and that's just bookwork that the transformer can only work with AC because it only reacts to changes. The coils in the transformer only react to changes, so they cannot really react to DC voltages, they only react to changing voltages. Explain fully what the electricity companies do to reduce the energy loss in the transmission lines. So the first thing is that the voltage is stepped up at the power station, and that means that the same power can then be transmitted with a high voltage and a low current. The reduced current then means that less energy gets converted to heat in the transmission lines. Just the heating effect of a current flowing through a wire is reduced because the current's much lower, and that means that less energy is wasted as the power travels out to towns. So that's why we use high voltage, low current. Describe the role of transformer 2. Okay, so transformer 2's job is to bring it from the high voltage back down to the voltage that you would need in your home. And we need in our home, somewhere in the region of 220, 230, 240 volts. The mark scheme allows somewhere in that region. So 230 would be a nice value in the middle there to pick. So you just want to explain that transformer 2 steps the voltage back down to 230 volt for use in homes. And all of our appliances, everything you plug into sockets at home, require 230 volts, and the same for your lighting circuit. See, the diagram below shows a simple electromagnet. The switch is closed. At the point marked X, show the direction of current flow by drawing an arrow in the box beside it. So we need to identify positives and negatives on our power supply and then know a little bit about how current flows. So the long line in a cell is the positive, and that means that current is going to be flowing from positive to negative, so it'll flow away from the positive, which means by the time it gets to X, it will be upward. Part 2. On the soft iron core, mark clearly the magnetic north and south poles. Right, so if the current's coming up here, it's going to come up on the front of this coil. And it's going to come up on the front of all of these. So if we imagine ourselves looking down this end, we should see anti-clockwise current flow. Okay, so just think about that for a while. You would see anti-clockwise current flow. Now, to determine what end that is, we just take the letters north and south and add little arrows to the end of them. And you'll see the one that has anti-clockwise pointing arrows is the north. So when we see anti-clockwise current flow, that means that that is the north. And equally, if you were to look down the other end here, you would see clockwise current flow, and that corresponds to the south because it represents clockwise current flow, belongs to south. So north at this end, south at that end. The circles represent the position of a magnetic compass. Mark an arrow in each of the circles to show the direction of the magnetic field at each of those positions. Right, well, so magnetic field is always the way a north pole would be pushed. Well, a north pole would be pushed away at this end, and it would be pulled in at this end. And so it's going to come out and make its way around. So it's going to be that way here, heading over towards the south. And that's also going to be true here. It's going to be heading that way. So field leaves at the north, heads around and enters at the south. So these arrows all have to be consistent, coming out here, heading that way, going in there. Coming out here, heading that way, going in there. So the arrows can't disagree with each other. Part 4. The wire used to wind the coil of the electromagnet is insulated. Explain why this must be the case. And so the idea here is that you want the current to flow within the loops that you've made, not across through them. You don't want the current leaking through and not making loops around the core. You want loops of current around the core, not it running down sideways through all the connected bits of coil. So if you think about, this thing, if these touch each other and you get current just running down through their touching edges, that's not going to produce loops of electrons, and it's the loops of electrons going round that make this magnetic field. Okay, so you're going to want the current to flow around the core and not have short circuits, reducing the looped current. And you certainly don't want it making contact with the iron itself and the iron starting to short circuit the coils and losing all your strength of magnetism. So the coils touching each other would produce short circuits. The iron touching the coils would produce short circuits, and in both cases they would reduce the amount of magnetism produced, because it would reduce the amount of looping current that's going around the iron. Okay, so if the coils touch coils, you're going to get short circuits. If the coils touch the iron, you're going to get short circuits. And we want the current to be going around the iron in loops to produce this magnetic effect, not through the iron. That doesn't help us at all. And that's the electromagnetism question, question 4 done. Thanks for watching.